So that gets you into this diagram that I showed on the previous slide, where, you know, the states don't move a whole lot, they don't change a whole lot, but the resonance width has changed dramatically. So the central resonance is now the most narrow one here, C1, and you see it slightly modulated when it crosses the emitter bound state E2, which has a much broader width that's up here. And they interact with each other, coupled resonator problem, bonding, anti-bonding states, they couple to each other and they change the resonance width a little bit. And again, what you see now is the central resonance C1 being pulled by the central resonance E2. And you should see a current peak there. And now the resonance C1 is also pulled past E1, and you should see a resonance here. So let's look what we see in terms of current. So without the relaxation in the reservoirs, indeed, we see these two current spikes, right? There's one spike here on the left and sort of in the thin line, and another spike here. But if that relaxation is set to 6.6 millielectron volt, all what's remaining of that first peak is actually a little bit of a shoulder. And the main current is actually flowing through the emitter-bound state E1. And then the current drops, and then the current rises again. Okay? So in a sense, what that relaxation does, it washes out, so to speak, the sharpness of this resonance, and it broadens it, and it allows it to be broad enough to supply enough current here at the peak current. Okay? Key element here is that the central resonance C1 is almost unaffected in its resonance width, that the emitter one is significantly broadened to over 6.6 millielectron volt, that the relatively narrow resonance is probing the states in the emitter, just like what we had before. And since this resonance E2 now is much broader than it used to be, it carries much more current. And it's, in that sense, a scattering enhanced current, but it's the scattering in the emitter that is important. It's not the scattering in the central resonance that's important. It's the scattering in the emitter that determines the peak current here, because it's determining the spectrum out of which you inject carriers. So now if you show the same plots of what I had shown before with where eta was 0, so here is the constellation of resonances with at a bias of 0.32 volts, which before started with eta equal to 0 corresponds to this current peak here. And this is the same current density plot I had shown in the previous lecture, where C1 couples to E2, and all the current is flowing through that transition path. Now if I plot the transmission coefficient times the current, so modulated by the Fermi functions, that's the current density, you sort of see a little bit of a shoulder left of E2, whereas here it was a very sharp resonance. Now it just turned into a shoulder, and the current is all flowing in the ground state C1 to E2. Okay? If you crank up the voltage further to 0.42 volts, now you're aligning C1 with E1, and the current density in the eta equals 0 case now looks like this. We've seen it. And there was a little bit of relative current flow of 10% or so here in the C2. And if we now turn on eta to 0.6 volt, to 6 millielectron volt, what we see is that little hump here that was due to E2 gets sort of absorbed in the broadened current density, and almost all the current is now flowing, all the normalized current is flowing through C1 and E2. Again, the green line is normalized to 1 to the total current. So probably the absolute current flowing through the second state is probably the same. It didn't change. It just is now being dominated by the current that flows through the ground state. Okay? So again, the green lines show you very nicely where in energy the current is flowing. So now let's crank up the voltage further to the valley current. So I'm going to 0.76 volts, it's roughly here, where the RTD is again turning on. And what you see is at eta equal to 0, so that darker IV curve, you have the central resonance C1 is right at the bottom of the emitter right here. It is under E1, and E1 was very sharp, so it has a very sharp resonance here, but there's no current flowing through that resonance. And then E2 has a broader resonance, but you know, there's a little bit of current because this green line here and has a little bit of a slope. But really all the current is flowing through C2. Right? So for this dark line here, the thicker line, all the current is flowing through C2. Now, if you have an eta of 6.6 millielectron volts turned on, what you see is something that is slightly different than the eta equal to 0 case. What you see is that there is actually current flowing at C1. So C1 is actually probing the tails, the energetic tails of this resonance. And still there's a little bit of current flowing, and it's roughly, if you read it off, here roughly should be 20% or so of the current is still flowing through C1, scattering enhanced of the emitter. There's a little bit of a bump in E1 and E2, but not much current flow. And then there is current flow in C2. That's why this current here is still a little bit bigger than the eta equal to 0 case. Okay?